Let me start. So, in last two class, Professor Kari continued with chaos and other things. Before that, we were talking about non-uniformity in Cellular Automata. In that part, we have seen three ways of non-uniformity, which have been introduced in the classical Cellular Automata. So one is asynchronism, where cells can be updated independently. This is asynchronous cell automata. Another was automata network. Instead of considering a uniform grid, cell automata are defined over a non-regular network. Okay, so that's also another kind of non-uniformity. And third, we have talked about hybrid cell automata or non-uniform cell automata, where different cells may use different rules. So today we are continuing with that part, third one, non-uniform cell automata or hybrid cell automata. Okay, so by non-uniform cell automata, we generally mean hybrid cell automata, right? That is, the cells of an automaton are using different rules. Okay, so we shall discuss this kind of cell automata in detail. This class and coming few classes, we shall discuss about this kind of automata only. Let us start with a generalized definition of this kind of cell automata, non-uniform cell automata or hybrid cell automata. So there is a chance of confusion that while we are talking about non-uniformity, then we are talking that asynchronism is one kind of non-uniformity, automata network also another kind of non-uniformity. So in that sense, all are non-uniform cell automata. However, in literature, by non-uniform cell automata, generally, hybrid generally we mean hybrid cell automata, right? So this convention is followed over here, right? Anyway, so here there is a definition, generalized definition of non-uniform cell automata. A non-uniform cell automaton, sometimes we call it NUCA for non-uniform cell automaton, is a quadruple. Recall that CA is also a quadruple. The same is here. It's again a quadruple. First one is L, is a d-dimensional lattice. It was the same like before. And S is the finite set of states. And next, M V vector V and R vector V. So these two are different. Here M vector V, here V is any element, is an element of L, right? And for each of V, we have M, neighborhood vector, and a rule, right? This is the property of a non-uniform cell automata, right? For each V, for each cell actually, V here is a cell. For each cell, we have a neighborhood vector and we have a rule, right? So here, MV is, as usual, it is V1, V2, Vm, right? Is a neighborhood vector of V, right? and R V is a rule from S to the power m to S for the cell V. Note that here for cell V, there are the cell V is dependent on m neighbors. Okay. For cell say another cell say X, that may depend on m dash number of neighbors. Right. Since rules are changing, so neighbor dependency may also change. So what is written here, m and r for a single V. Right. So this is the generalized definition of a, non-uniform cellular automaton. Right. You understand that? See, when rule changes, then neighbor dependency can change. Right. For example, if you consider one DCA, one cell may depend on left and right. Right. Other cell may depend on left self, and may depend on say two neighbors on left, two neighbors on right. These are allowed here. Right. These are allowed here. So so this is the most general definition of non-uniform cellular automata, but really it is too general. Okay. It's too general to deal with, right? So it's infinite. If I consider L equal to z to the power d, right? If L is infinite, right? If the grid is infinite, then yes,
Sir,
yeah, please.
for each V, we have M and R. Means it
Right,
is specific to each of the cells.
right.
Now, if it is infinite lattice, that means for each of the cells, we have to individually define the neighborhood vector and rule vector. It is not like we are taking the maximum of the number of neighbors and we can use that as the general neighborhood vector for all the cells. It is not like that.
No,
Okay.
it is not like that. I mean, isn't it clear from this one?
So actually, I got confused because by in the definition, if we are mentioning only about V, that means M and R both are then becoming sets, right?
M and R
Set of
becoming
set of sets means M will be a vector. So each of the M's are vectors. So we'll be getting actually by M we are mentioning about only one cell. So in the definition, it is specifying about one cell only.
right, right, right. Arbitrary for arbitrary V and two for all V.
Yeah,
Right.
but for all we, how can we say this from the definition?
I'm not getting the point.
Means
But
where this MV,
yes, M.
this MV, this is for any arbitrary V. So if we take any other V, then this neighborhood structure will be changing. But number of neighbors, is it less or equal to small m, or is it? It
No,
can be.
it's different. It's different. It's different. It's different.
Okay.
Actually, I should write logically, right? For all V, there exists an M, there exists a vector like this. Okay. So if you think in math in the terms of logic, so
Hmm.
right for all V, uh,
So
there exists.
actually, four tuples means one entry in the tuple, that is a set itself, set of vectors.
Sorry, which one?
both M and R, these are not, these are single entries, it seems, but
Right,
actually
right,
these are sets.
right, 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 right. I got your point. I got your point. So you're saying, although I said it's quadruple, but it's MV, this is for individual V. So if there are many V, obviously there are many cells. For each
Hmm.
cell, I take many vectors, number of vectors.
Actually, if it is infinite set, then all these two sets will be infinite sets.
Right, 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 right. Yeah. Uh, I mean, if you could talk about set, right?
Hmm.
Then R, the set of rules become infinite, because you see, because if you have, say m neighbors,
Hmm.
suppose m is a maximum value. I'm talking about that. So, but it is finite, right? So possible number of rules is finite, right?
Yeah,
So,
but
uh,
possible number of rules, but here we are mentioning about every individual cell. That means for if we are defining a lattice over infinite, like it is if
mm,
it is subset of z to the power d, that means that set becomes an we can't say set probably. It will
right,
be
sequence,
order.
right? That is infinite. Yeah,
Set will be finite, but
right.
if we say in terms of order tuple, then it will be again infinite.
Yeah. If you consider sequence of rules for individual cells, that is infinite, right? That's right. Hmm.
Okay, thank
Yes,
you.
okay. Hmm. Uh, but what you have pointed out, it's a very important thing. Although you have not said it, but probably you have meant it. That how can we deal with such infinite set, right? In my previous cases, in my classical cell automata, it was infinite, git was infinite, but rule was single rule, and aim was, neighborhood also vector was, single one, right? Single one, single neighborhood vector was there. But here, both infinite. So how can you deal with that one, that kind of CA? It's really very difficult. And we'll see that almost all issues, all problems regarding relating these to non-uniform CA, they're all undecidable. Okay. If I consider lattice as infinite, and if we rely on this definition only, then, for example, reversibility, we have seen in previous classes that for one-dimensional CA, reversibility is decidable. But even if I take L is a one-dimensional lattice, but if it is only from CA, it is not decidable. Okay, so many issues, many problems, they are undecidable here for non-uniform solar automata. So really, it's too general definition to deal with. We shall see that actually, if we look at the history, we shall come to this point later, that non-uniform solar automata was developed in late 80s, and at that time, only finite series are considered. This definition, this kind of definition, I mean, we get this kind of definition in, say, 2008, 9, during that time. The group of Enrico and his colleagues, they have defined in this way, and it's most general one. Okay, so the almost all works that deal with non-uniform cellular automata, they do not work with this definition, right? I mean, it's the most general one. So I have written here just two general definition to deal with. And this definition, this is for d-dimensional lattice. And most of the works on non-uniform cellular automata, they are for one-dimensional lattice. So here also you consider, so our lattice equal to one-dimensional. Now suppose L equal to Z, right? Then I can write my non-uniforms in this fashion. Z is Ri, R is radius. See, recall that neighborhood vector is one way of defining a CA. Another one way was the radius, using radius. We have discussed this part before. So here I have used radius, the same meaning. So radius is different. So here Ri, small ri and capital Ri. Capital I is the rule of cell I, and for that rule, radius is small ri. See, this is one dimensional array. Say this is the ith cell. Say so, this cell depends on ri number of neighbors in left and ri number of neighbors in right. Right. So this is the meaning of uh, the radius. So for this class of CA, three subclasses were defined. Let me talk about these three subclasses. We sometimes call them d-NU, d-NUCA, p-NUCA, and r-NUCA. So these three names were given. They are the subclasses, right? Why these subclasses were defined? Because of because we cannot deal with non-uniform automata of this general type, right? So if you do not know a particular arbitrary cell, what that cell it is using, I mean, which kind of rule that cell is using, then you cannot get the next configuration, right? You cannot evolve the system, right? So we have considered here three subclasses of non-uniform C. This is d-NUCA, p-NUCA, and r-NUCA. Note that these subclasses are also defined for one-dimensional lattice only. So here I have considered L equal to Z. You can see here. Okay, right, right. So say it is d-NUCA. What is this d-NUCA? So let me define it first, then we shall discuss in detail. This is the definition. So it may look difficult. So there exists a k and r in n. So two natural numbers k and r, and h is the rule from x to the power 2r plus 1 to s, such that r equal to h and r equal to r for all I in Z, where mod of I greater than k. So d-NUCA is simplifying the original definition. How it is doing so? See, suppose this, if you consider one this here, suppose this is my, this is the length of this is my k. So k is a number. So 0 is my origin, right? 0 is my origin. So z is positive in x along with the x-axis, positive numbers and negative numbers, right? So in this part, the cells may have, I mean, cells may use the arbitrary rules, different rules. But beyond this limit, all the cells use a single rule that called H. Right. Now understand. So this is much simpler than the previous definition. In previous this definition, it was said that any cell, I mean a cell can use any rule, right? And any neighborhood vector it can use, right? Here I am saying no. Consider a finite amount of place. In that place only, the cells can use their rules of the choice. But beyond that place, all the cells use a single rule that is called H. Right? It is very similar to the finite configuration. Recall that in a classical CA, what is the finite configuration? See, a finite amount of cells, they were in non-cohesion state, and rest are in cohesion state, right? So if you can recall, So finite amount of cells, they are in non-cohesion state. The similar type of idea is here, that in a finite amount of places, the cells can use arbitrary rules, different rules, rules of the choice. But beyond of that place, you know, all the cells, they use a default rule, and that default rule is the age. So when I'm defining this d-NUCA, what I need in the definition, I have to say value of r, value of k, as well as this age, that you have to specify. Then you specify in the other places. I mean, in that finite places, for the rules to be used by the CA, right? So this is uh, d-NUCA. A
Sir,
general, yeah, please.
sir, why we are writing H? I mean, instead of H, if we directly write Ri such that 2 to the power 2r plus 1 maps to S, I mean S to the power 2r plus 1 maps to S, will it be different? Because why we're, I mean, is there any reason behind writing H and then Ri equals to H?
See, Ri, R actually I have used in the definition. For cell, R is the Ri is the rule of cell I, right? So
Yes.
definition, it is R vector V. So here since it's 1D, if I cell I, so Ri is used, and I is any cell,
No,
right?
if we do not write H, then will it be different?
Then you can write then, but the point is, uh, uh, no, I mean your writing will be difficult. It's possible. You are
Yes,
saying,
I mean both are same, right?
yeah, yeah, it's possible. It's possible. I think it is, it makes this definition. I can write in one line. Uh, uh, but if I follow that one, I need more quantifiers, and it's possible.
Okay.
It's possible. I mean, so although I'm saying RI, but all RI is same. So I can write
Yes,
RI
yes,
equal to RJ equal to this. Then I have to write these things. So I have to
okay,
specify. No, beyond that finite place, the rest place they are using same rule. So how I can write RI? I'm saying RI and RJ. So I'm not equal to J. RI not may not be equal to RJ. Then I have to
yes,
write. No, it's not a fact. RI equal to RJ.
yes.
But yeah, I have said the H single rule, right? And
Mm,
all RI they are using that H, the same rule. Okay, but
okay,
same rule except that finite amount of places,
yes,
right?
yes. Thank you.
So this is the d-NUCA here, and we can generalize this definition here. What I'm saying, that in the left hand side and right hand side, all are using the same rule, right? All are using the same rule, the default rule. But what I can say here, the left hand side using one set of rules, right hand side using another set of rules. So if we generalize this, then I get p-NUCA. It's like this one. So it is saying that, so like before, sorry, like before, in that middle place, finite amount of place, the cells can use arbitrary rules of their choice, but left hand side and right hand side, same set of rules are applied. Here, see, here an important thing is Ri equal to R I plus P is written, right? So what is the meaning? So let me go to that one. Let me go to the Jamboard. Where is Jamboard? Let me go to the Jamboard. Okay. So here, what is said here? See here, say in case of r-NUCA, suppose this is cell 0, then cell 1, this is say k, and this is -1, this is -2, this is -k, right? Now here in this place, in case of d-NUCA, in case of d-NUCA, only in these places, only in these places, the cells may use different rules of the choice. But beyond this one, say all the cells they are using H, all the cells they are using H. So H is the default rule. This H is the default rule, right? So here this is the d-NUCA. Now, in case of p-NUCA, its demand is different. What is saying? So here it is saying that, okay, let me use a different color. Let me use the, yeah. It is saying that some rule is applied here, then some rule is there, some rule is there. So a p times this rule is applied here. So similarly here, a p times a set of rule is applied. Now this sequence is repeated over this lattice, over this right hand side. This part is again repeated here, again repeated here, in this way. Similarly, in the left hand side, this part is repeated, and so on. Okay, so here also this p. So this is, we call it p-NUCA, right? Now here, what I get, actually I get, say for Ri, so if I consider a set Ri where I less than, say I greater than k, I am saying I greater than k, one set, I can get another set when, say I less than k, I less than minus k, right? I can get two sets. Acha, p-NUCA is not saying that these two sets are same. What it's saying, periodically these rules are applied, one in right hand side, another in left hand side. So therefore they may not be equal to same, right? They may not be equal to same, and we get two sets here. One is for the right hand side, another is for left hand side, right? Which are applied periodically. Right? So this is the p-NUCA. And why I am saying that, why I am saying that the generalization of d-NUCA, because if I consider they are same, if I consider that actually this set is equal to H and this set is equal to H, okay, I mean this set is actually H, only one rule is applied. Yeah, what is the value of t that was mentioned? It can be 0, 1, 2, or any value, right? It is any value, right? Now, if t is equal to 0, means the next time again this rule is repeated, right? When Ri, this set will become this set H, and this set will become this one. Then in this case, there will be same. and it will be d-NUCA. So p-NUCA is a generation of d-NUCA, or from d-NUCA we can get p-NUCA. Okay.
Sir, for PNUCA, that means we have total three set of possible rules.
Sorry, three set of means, or for this one, for the middle one.
Minus K, okay, we have another set of rules.
Yeah. Actually, see, in these two definitions, what we are doing, practically we cannot deal with infinite non-uniform CA if we do not know the cells are using what kind of rules. Right. If it is completely arbitrary, you cannot deal with that kind of CA. So these kind of classes defined. Right. Here you can do. You know the left side rule, you know the right side rules, then you know. So left hand side, right hand side, they behave like uniform CA, right? Be it d-NUCA, be it p-NUCA, right? At least theoretically you can tell, okay, given a arbitrary cell number, I know in that cell this rule is. But if I give you arbitrary a general definition of CA, and give you arbitrary, if I ask you, you tell me in arbitrary cell which kind of rule is being used. Right.
We are also taking the neighbor as radius, a single radius.
Right. It's always true. Always we take radius. I didn't get your point. We always consider radius.
Yeah, means for d-NUCA and p-NUCA, the rules they are using the same radius. All the rules.
No,
So
no, no,
all
no, 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 no. That I've not said. That I've not
the
said.
radius can be different.
Yeah. See here, radius can be different. I have not said anything about radius. See here, see what I
But
mean
in
that.
the definition, you have used only one single r, small r.
No, Ri I have used. This is the definition. So Z, S, Ri, small r I, capital I. This I have used. The important thing is Ri and Ri. This pair is important. This pair is important. This I is a cell number, right? And in which cell, what kind of which rule is used for that? This is important, right? After this one,
So can you go back to the slide? I got confused actually.
have I used no? You can see
This small ri, what is that?
smaller
You
I.
said d-NUCA and p-NUCA. We are taking one small r, natural number.
This one.
Yeah.
Okay. This is saying, see, since age is, so this R is used in age.
Hmm.
So the default rule, na? If the rule is same, then R is to be same.
Yeah.
So I have written here singular. See, what
So
is
okay.
saying? For
Okay.
all I, for all I in Z with this one, this constraint, I, what is the value condition of I mod of I greater than K means I is greater than K or less than minus K,
Okay. So
right?
for the if there is one single rule, then obviously the radius will be same. But for the other rules, radius can be different.
Yeah. I'm silent about radius at this stage. d-NUCA and p-NUCA, I am silent about radius.
Okay. Thank you.
And if radius is same, if radius is same for all the CA, right? If radius is same, so if radius is same, say if radius is same, okay, this figure is meaningless in fact. 0, -1, 1, etc., etc. If radius is same, right? Say Ri equal to R for all I in Z. If it is true, then the CA becomes, then the CA is named as uh, r-NUCA. Sorry. Then the CO is called r-NUCA. The third one. Okay. So in case of r-NUCA, we write it in this fashion. That Z, then S, then only R, then Ri. Right? This is for r-NUCA. When R is same for all the rules. Okay. Now, as it is argued in last class also, okay. So you may argue that no, r-NUCA is the general one because I can take the max of Ri. Okay, you may argue this fashion. I know. Kamalika, what you're saying, you can argue that all are the same. Why? Suppose you consider max over Ri, right?
Yeah,
Okay.
yeah, that we can
Yeah.
do.
I belong to, sorry, I belong to L. Suppose you consider this R, you find this max, and suppose this is the R. Okay, and lastly also Professor Kari was arguing in this way that any CA you can consider its radius is R, right? Even if the radius is different, you can consider a uniform radius R. So if you consider it in this fashion, right, then then the old definition of non-uniform CA, becomes this uniform CA. Non-uniform CA becomes r-new CA of this type, right? That you consider, but we have not used this one, but you can do. Uh, so since you can do it, dealing of r-new CA is as difficult as dealing of the general non-uniform CA, right? Okay. Any query? Any query? So let me argue that almost all problems related to non-uniform CA, generalized non-uniform CA, they are undecidable. I have said also. See, consider this one, this figure. I'm not considering 2D, 3D, high dimensional CA, right? I'm considering one dimensional CA, the simplest one, right? One dimension has several advantages. Even in that dimension also, many properties are undecidable. For example, injectivity, surjectivity, and obviously reversibility, you cannot decide for an arbitrary non-uniform CA. Why? Because see, this is a distant neighbor. Suppose this is a distant neighbor. Say it is I, say I may be 1 lakh, 2 lakh, 1 billion, I don't know, any value, any I actually. So in this cell, some rule Ri is using that I know. I mean, some rule Ri is there. But what is the Ri? What is its definition? If you don't know, then you cannot find its behavior. You cannot get the next configuration of the CA, right? To understand injectivity or subjectivity, you should know, given a configuration, what is the next configuration. I am saying here cell I using Ri. But what is the Ri? If you supply me, okay, this is the Ri, then at least you can try. Well, for I know Ri, and then I'm trying to find out injectivity property or scientific, etc. But if I don't know Ri, right? If I don't know Ri, then how can I know the how can I decide the injectivity, selectivity, or other set theory properties of this CA? It is not possible. However, in case of d-NUCA or say p-NUCA, somewhere it's possible. How it's possible? Say, for example, for d-NUCA, I know if it is distant, if it is distant cell, so Ri is H. That I know in case of d-NUCA. In case of p-NUCA, if I know that one, if I know that the both the sets, then okay. By knowing the periodicity, I can determine the rule Ri. So in case of d-NU or in case of p-NUCA is possible, but if arbitrary NUCA is given, it is not possible. This is the reason why people have defined d-NUCA and p-NUCA. Okay, because otherwise, if you consider that definition, the arbitrary definition that any cell can use any rule, uh, you do not know. Although some effort can be done, you can take some effort, some so here the issue is, so like that Ri and capital Ri. So here you have to know the distribution of this Ri. Distribution is important. So p-NUCA or d-NUCA, it clearly states, it clearly talks about the distribution of the rules. But you somehow know the distribution, then okay, for arbitrary I, you can get that Ri. So point is here, you should know the distribution. You have if you have any other way, obviously there are ways to know the distribution of rules over the lattice, then it's possible. If you don't know the distribution, it is not possible, right? So this is p-NU, d-NU, and r-NUCA. Any query? Any more query?
So suppose we define the r-NUCA in this way, like for each cell, whatever rule we are applying, although it will be infinite set, but we say we are using a series of rules. The way we can define that is also an infinite series. Then can we say anything about the behavior of such kind of CA?
Repeat the question, please.
That this r-NUCA, that is the most general version of non-uniform CA, right? So in that case, say for the infinite lattice, we are defining the rules for each of the cells also, like in some using some formula. Say we are using a series to represent which cell will be having which rule. But in that case, can we say anything about the behavior of the of such a CA.
That might be possible. If you know that one, that might be possible. Oh, and, I'm not sure. I can't say in advance that we'll be able to do that one, but it might be possible. Right. It might be possible. Somehow, if you know, you are saying, for r-NUCA, the r-NUCA you're talking about, if you want to give the sequence of cells, that's also infinite. So that you cannot specify, right? That you cannot specify. So somehow some technique is needed. Suppose you have some algorithm. Suppose you have some algorithm by which you can decide that when rule I is given, then sorry, cell I is given, then I can tell you the rule I. If you can design such an algorithm, actually I'm talking about that particular only. When I'm saying no, these are d-NUCA, p-NUCA, some simple algorithms are there. But if I make it complicated, say an infinite C is given, you have to develop some algorithm, right? By which you can tell that rule of cell I when I is the input cell number. It is possible to develop some algorithm. Okay. Then for that kind of thing, you can know the rules, and then it's possible. It might be possible. I'm not saying it's possible. It will be possible, but it might be possible.
Okay.
Okay. Right. I mean, you can say that some recursive procedure is there, right? By which you are determining the cell and the rules of the cells. It's infinite. You don't know. Uh, uh, I mean, if you don't know, then you're gone. Okay. Well, so now, although it is obvious, so still I'm saying that that in this case also, for a CA, if even this kind of CA is given, suppose L, say S, M I, so MV, and then RV. Okay, if this is non-uniform C is given, so corresponding to this, you can get a global transition function G, right? Like before, you'll have the configuration. Here also a configuration. These things are very common, so all they're same. I mean the similar kind of definition. I'm writing it in. So C is a configuration. Small c is a configuration from L to S, right? This is a configuration like previous, the same bit classical C, bit non-uniform C, the same. This is the this is a configuration. Okay, this is a configuration. So if I consider S to the power L, what does it mean? It is the set of all configuration. Set of all configuration, right? Right. So therefore, so I can consider that a CA hops from one configuration to another configuration. Finally, CA is a discrete dynamical system, right? Time and space both are discrete. From one configuration, it goes to the another configuration, and for that also we are defining the rules. So, when I note this one, then from this one I can get a global transition function G. So it is from h to the power L to h to the power L. Okay, so G is the global transition function of this CM. So how can I find out G here, right? How can I get this, this G? So suppose this, suppose it's like this. Suppose say X the configuration, right? X the configuration. X is to the power X is a configuration. So G of X is equal to Y. Y is another configuration, right? So Y equal to Gx. So since in case of CA, I get the next configuration by applying the local rules. How can I get that local rule? Say how can I get that local rule? Say I'm considering here in this way that say Gx, I am to find Gx for an arbitrary cell V I am to find, and in case of V I was having, the cell X. Okay, so it was having the configuration. So here in the configuration, so it was having that cell X. Sorry, uh, how can I do? Okay, okay. So here at cell V, so configuration is X. So X at cell number V, what is the value of this? So configuration was a function, and V is the cell number. It is a state. What I can get? State of this one, right? Now this cell, say either M neighbors. So right. So configuration X, I'll have so V plus V1 is state of this cell, right? Now here X of V plus V2 is another state, right? It is having another state, right? Now on that state I shall apply this R. Now what R is having? So in this R, just let me write it. I shall write here X of V plus V1 plus dot 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 plus X of V plus Vm, right? The other state, okay. And here this I should write not write R here. I should write R actually. This is the rule. R is the rule at cell used by cell V, right? Now here I can get for the given configuration X, I can get the state of these cells, right? V, its neighbor is V plus 1. So V plus 1, V plus V1, this is a new cell. The state I can get using this one. X is a function, is configuration is a function. And in this way I can get the state of M neighbors of V. Over that I'm applying R. That is equal to this one, right? That is equal to actually G of X V, right? That is equal to actually Y at V. So this is a relation, right? This is a relation. So when x is given, when x is given a configuration, from that x, what I know actually, I know the state of all cells. Now each individual rule takes as input that states of the neighbors, and they find out their next state, right, using that applying the function. So this is the function. In this way, non-uniform cellular automaton, find out configuration. Note that if it is uniform CA, then please recall that in that case we have not used this one. Why? Because all the cells use same rule. Rest part is same. This is the only difference. That is not applied. No, that is not used. Now, since all the cells use same rule, by knowing the configuration, when a configuration is given, I can get the next configuration. In this case, I have to know the configuration because it is given to me. Okay, as usual, I have to know that one. Additionally, for individual cell, I have to know you know the rule, right? Okay. Let me go back to the slide. Okay. So now we were talking about arbitrary infinite case actually. C was defined over infinite lattice. Now we come back to our finite case, right? Historically, most of the works, almost all works, better to say, but almost all works that deal with non-uniform CA, these CAs are finite. Number one. Number two, almost all works there, they use one-dimensional, lattice. So these two cases, whenever it is a question of non-uniformity, or sorry, in case of non-uniform CA, almost all works, they consider, uh, you know, one-dimensional finite CA. Although there are some works, even we have some work on non-uniform CA with for two-dimensional, but these are the rare one, right? So here in this class also, in this course also, we shall mainly concentrate on one-dimensional case. Okay. Now, when it's one-dimensional case, then we define a new term. Although we have introduced in the last class, they are called. This is called rule vector. Okay. So now this is the definition. A rule vector of an n-cell NUCA, it is LSR. Ri is R0, R1, Rn-1. Okay, where n equal to size of lattice and Ri is the rule used by the cell I. Notice that here CA is finite, therefore L is finite. Fine. And we always consider L here a set of 0, 1, 2 in this way. It's a natural number. In our coming classes also, we shall never consider that L, consists of any contains any negative number. It starts from zero always, right? And it is required. It has some theoretical reason also. That I'm not saying here, but uh, note that when L is finite, I consider L is a set. It starts from zero. Means in a cell number, we starting numbering cell zero, then one, then two, then three, and so on. And so, if I have n number of cells, here n is a finite number, right? So then I get a sequence of rules, a vector I get. This vector actually defines the CA, and this vector is called rule vector of rules, right? So it's obvious, I think. Next, another important special class called non-uniform CA. Okay, we are specializing, we are simplifying our case, simplifying our system. First, infinite CA, no, from infinite to finite, right? Then finite to non-uniform CA. Now, what I'm saying here? I'm saying here that each cell uses only Wolfram's rule. So it means that the cells are using ECA's rules only, and that is called, non-uniform ECA. Historically, non-uniform CA was first studied for this class of CA. Okay, it was in 1986 when non-uniform CA or hybrid CA, non-uniform CA under the name of hybrid CA, its name was, hybrid CA. This class of CA was studied like praise. Okay, so interesting work, but no, this is the first work on non-uniform CA. And after that, throughout the 90s, many works, you can find many works. All these works use this non-uniform ECS. Most studied C for application purpose actually. This class of C is the most studied C. Most studied CA for applications purpose. Even today, when people try to use CA for some application purpose, so for example, pattern generation, random number generation, cryptography, or other cases, so then this class of CA is used. Take an example of four cell non-uniform C. This example I have given 15090, 15090, right? So let me recall it again. Let me recall it again. So this is called rule vector, right? Here rule vector we write in this fashion. There are four, four cells, right? Four cells, so four rules. So what does it mean? Here you see that 15090, first is 150. That rule 0 is R0 is actually 150. R1 is 90. R2 is 150, and R3 is 90. In this way, we write, the rule vectors, right? Since it is finite CA, we have to define the boundary condition, right? So popular boundary conditions are open boundary and periodic boundary. For open boundary condition, most studied boundary is the null boundary. Interestingly, you can see that for this non-uniform ECAs, for this class of non-uniform CA, most studied boundary condition is null boundary condition, right? Okay, can you recall, or should I show this one how it works? Should I test it again? Okay, are you here? I can see you. Are you here?
Yes, sir, we are here.
Okay. Just just a sec. Just a sec. Just a sec. আচ্ছা ক্লাসে আছি হ্যাঁ হুম হুম কোনটা আচ্ছা ঠিক আছে হ্যাঁ 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 আমি ক্লাসের পর করে দিচ্ছি হ্যাঁ ঠিক আছে সরি সে রুল so rule 90 150 0 1 0 1 1 0 1 0. This is if you this is the style of presenting a rule, you know. It's a ECA is thin about CA, right? Can you recall ECA is thin about CA? ECA, in case of ECA rule, let me tell you again. In case of ECA rule, it is 0 and 1, okay, and R equal to 1. So three neighborhood. So actually, a rule, any rule R, it is from S cube to S. Why? Because 2R plus 1. A cell depends on left neighbor, right neighbor, and cell. So three neighbors. Okay. So this tabular form, the first row represents the combination of states of neighbors, right? So this is the left neighbor, this is left neighbor, this is self, this is right neighbor, right? In this way, this is left neighbor, this is self, this is right neighbor. What I'm saying that what I'm writing here, if left neighbor is 0, self is 0, and right is 1, then it is 1, right? If all are 0, sorry, it is L S R. So if all are 0, then it is R 0 in this way. So in the tabular representation, we write down first all the all the states of neighbors first, right? I mean all possible states of neighbors. It's called, sometimes we call it neighbor configuration. Then for each neighbor configuration, we write the next value. So this defines the rule. So, and Wolfram style is you represent this rule in decimal format. So it's a 8-bit sequence 0 1 0 1 1 0 1 0. 8-bit sequence. Its decimal, I mean, representation of this binary sequence is called rule. So it is rule 90. You can do it. You can check it. And 150 is 0 1. So I know it before, so I am writing in this fashion. Otherwise, you have to convert it from decimal to binary. So 1 0 0 1. So it is 150. So two rules. And what is my rule vector? My rule vector is 150 90 150 and 90. Boundary condition is null boundary condition, right? Just I shall tell you I mean how the steps are being executed. So consider my initial configuration is 0 0 0 1. Four cells, right? Four cells. So in initial configuration, you have it's size 4 actually. The size of length of configuration is 4, so it's 4. So okay. So here is null boundary condition, right? So in left hand side it is 0, right hand side is 0. Both are 0 because of this null boundary condition. So 0 0 0. First rule is 150. For 0 0 0, it is 0, right? Then next rule is 90. Next rule is 90, right? Then it is 0 0 0 again. For this one also, next state is 90. See, when I am finding the next state of a cell, two things I am considering here: the neighborhood configuration as well as the rule. In this case, it is 0 0 1, right? This cell depends on left neighbor, right neighbor. This is the property of ECA rules. So 0 0 1, right? And rule is 150. Come to this table: 0 0 1, result 50, it is 1. There is 1 here, so write 1. Then 0 1, what is this? This is 0 because I am using null boundary condition. So 0 1 0, and rule is 90. So 90 and 0 1 0 is 0, right? So from 0 0 0 0 0 1, I get 0 0 1 0, right? That's in this fashion. From this way, so it's an automaton, so it will run automatically, right? So then if I, so this is time step 1. Okay, see here the system is synchronous, right? There is no synchronism, system is synchronous. See, all cells are updated simultaneously. Okay, so you can see as if it is time step 1 actually. It is time step 0. So if I plot time step here, it is time step 0, time step 1. First time step, I get this one. Time step 2, what I can get here? So 0 0 0 again 0, 0 0 1. This is in second cell, which will I'm using 90. 0 0 1, it is 1. 0 1 0, it is 150. So come 0 1 0, 150 is 1, 1, and 1 0 0, 1 0 0, and rule is 90 here, and it's 1 0 0. It's 1, right? In this way, right? Should I do one more? Okay. So in this, yeah, please.
No, no, it's fine.
Okay. Okay. So in this way, from initial configuration and considering the rule vector, I can find the configurations, right? Okay. Now here, see, so I'm from one configuration, I'm moving to another configuration. From that configuration, I'm moving to another configuration, right? If I represent this successor periodization in graphical mode, then I get a graph. That graph is called transition diagram, right? Oh, okay. So if I represent them, this pre-successor relation to some graph, we get a transition diagram. And for this CA 90, 150, 90, 150, 90, we get this kind of transition diagram. Very interesting. You can see it's a very interesting diagram. Why is it interesting? You see, except all zero, all the configurations for a single cycle. It's a very peculiar behavior, better to say very interesting behavior. Okay, people, especially the C researchers, were fascinated with this behavior. Okay, they have explored this kind of behavior, and this is called maximality. This kind of behavior, whether if IRC is given and all the configurations except one will be in a single cycle, you cannot get it in case of classical CA, right? In case of classical CA, you can't get it, right? Even in case of periodic boundary condition, you can't get it. This property, this behavior we observe in case of open boundary condition. Okay, and this kind of CA is called maximal length cellular automata. This kind of these CAs are called maximal length cellular automata. We shall discuss about this because this class of CA, this kind of CA, has a different application, use in different domains, right? Next, we are talking about, we shall talk about linear cellular automata. Here, linear cellular automata means I am to mean linear non-uniform cellular automata, right? So this linearity we have also covered while you're talking about finite cellular automata. So a CA is linear if it is global transition function is linear, right? You know, what is that? Means that if the G is linear, if the G is linear, then the CA is linear. It's a simple one. It's a definition of linearity of a CA. Now, what do we mean by this linearity? Okay, let us consider two vector space W and V over a field K. Now consider a function f from W to V, and it is linear if two conditions are followed. One is the additivity, another homogeneity. Okay, additivity is, I mean, if x plus y, where x and y are two vectors of W, they're equal to fx plus fy, right? And see here, you can see here it is if x plus y, it is fx plus fy, right? This is the additivity. If this condition is followed only, function f is called additive function. Okay, and what is the homogeneity? Here homogeneity with degree 1. Say alpha is a scalar, right? Alpha is any scalar and x is a vector of W. And if homogeneity means, see here, f of alpha x is equal to, say, alpha to the power m for any m, right? Or say alpha to the power k dot fx, right? So this k can be any value in a natural number. If this is followed, then it's called homogeneous. The function is homogeneous. And what is called degree 1? Degree 1 is this k. If this k is 1, then it's called this degree 1, right? So here it is homogeneous with degree 1, means f of alpha x equal to alpha into fx. So if these two conditions are satisfied by this function f, then function is called linear function. Only first one is considered. If the first one is followed but not second one, then it's called additive one. Okay. Now here in our case, For linear CA, we consider the configuration space as vector space and the configurations as the vectors, right? For example, if you consider, say, binary CA, then we can consider the configurations are the vectors over, say, GF2, right? So field is GF2, Gauss field 2, right? So in that way, okay. So what I want to mean here, that configuration space is considered in this case as vector space, and the configurations are the vectors. Now, if a CA, if G, see, G is our global transition function, capital G. So G from sort of configuration, sort of all configurations to sort of all configuration. Now, if that G, okay, if the G follows these two conditions, additivity and homogeneity to degree 1, we call that function as linear function. If only first one is considered is followed, then it is called additive function, additive CA. Okay, now it's a theorem. Okay, this theorem we have proved also in a different fashion, that the previous theorem was CA is linear if and only if the rule R is linear. Okay, so it is similar like before. Here I am saying a CA, right? A CA, L is Ri, R small ri, capital Ri is linear if and only if for each I in L, Ri is linear, right? That I'm considering here. Okay. So, for simplicity, you may assume that L equal to Z. I mean, it is a one-dimensional CA. So this is true for finite CA as well as infinite CA. Okay, this is true for any L. Okay, it is not lattice size dependent, right? So if each Ri, each rule is linear, then the CA is linear. As even on leaf. So first assume that CA is linear. So if and only, so one way is you first assume CA is linear, then prove that each rule is linear, right? The reverse one is consider all the rules they are linear, then you prove that the CA is linear, right? So here I have given the outline of the proof. You consider, any say any say I any say cell of L, right? So for that you consider two neighborhood configuration, s1 dot sm, s1 dash dot h1 dash. What I have to prove? I have considered G as linear. From that, I have to show that Ri is linear. Ri is arbitrary. So if I can show that Ri is linear, then it's true for all I. So first is additivity. Here I have taken Si to Sm is one neighborhood configuration, another is S1 dash to Sm dash, another neighborhood configuration. Okay. Now this is, what is this? This is actually a configuration, right? Now you see here, by doing this, what I get? What is the value of G? Please recall that how I get G. G I get using Ri. Okay, I get G using Ri, and here this I can write here from S1 SM. I get it from configuration C, and this S1 dash to SM dash I get it from C dash. This I get from C dash, and this is applied over I, cell I. Okay, let me go to the proof directly. Let me open that part. Yeah, can you see it? Okay,
Yes, sir.
yeah. Here it is written. Okay, see here. Although this in this proof I have used just ri, the similar similar meaning. So for arbitrary I, oh, it is giving, oh, the same thing. Okay, so for arbitrary I, right? So this is I have considered this is, so I have taken these two neighborhood configuration, right? Now for these two neighborhood configuration, that what is written also in the slide. So for ri, just I have started from this ri, where this one is here, this one is here, this one, right, this one, and that one, and I am writing here this is equal to this one. How? So recall that how we find this g. How we find this g? Say g of x. Oh, it's very bad. So how we find this g? This is equal to, I have to go to Jamboard. Okay, it's not working. Maybe in this, yeah. So how we find this one? From this page, from this one, right? So in the right hand side, I have written R of this, the configurations. So what is this? This is the neighborhood configuration. So as input, the rule has taken state of all its neighbors. From that I can get this gx. Now if I write gx plus y, or x plus if I write gx plus y, then what I'll get? If I from this one, if I write gx g x plus y, then yeah, over this place, then I have to write this one. What is written here? Then this is for x, right? What is written here? I have to write here. Then similarly for y part, I'll write another thing. So similarly v plus v1, etc. The same thing I'll write, right? So if I write here x plus y, then within r I'll have two arguments. In other word, in the r, if I get two arguments here, okay, two neighborhood configuration within r, then I'll get two configurations which are applied and precision to this cell v, right? So this is written here. This is written in this proof, right? Okay. So here from this one I get g of c1 plus c2 to configurations, right? Now since g is additive, that I've assumed, From this one I can write g of c1 at I, g of c2 at I. Now g of c1 I means, if I expand again, I get this one plus this one. So what I get r, if you consider this is x, this is y, then I get r of x plus r of y. So it's additive. So r is additive. Now since I have chosen I arbitrarily, this is true for all the cells. So therefore, if my G is linear, then G is additive, then Ri is additive. So what is the next part? Next part I have to show that it is homogeneous. The similar way, you take in alpha. Alpha 1 is S. S is my, alpha is a scalar. Then what I show? Alpha 1 into the similar fashion, Ri, and then this X, this part I have considered, this neighborhood configuration here. Then what I get? Alpha into similar way, G of Ci. In this C, I have used here their X, but here it was used, written as C, the same meaning. So here G of C, relaxation at I, then alpha. Now since G is linear, hence G is homogeneous with degree 1, so alpha 1 into G of C, I can write G of alpha 1 into C at I, right? So now if I expand this part, I can get G of alpha 1 C, then I can get Ri, then alpha 1 into this neighborhood configuration, this vector in fact. So what I get? So I get that Ri is homogeneous with degree 1, because alpha 1 into Ri is equal to Ri, alpha 1 into Ri, say X it is, say it is X, as usual you consider it as X. Alpha 1 into Ri X is equal to Ri alpha 1 X, right? That I get. So it is homogeneous. So therefore, if G is linear, then Ri is additive as well as homogeneous. Hence, uh, Ri is linear, right? So if G is linear, Ri is linear. Now in the reverse way, we consider that each Ri is linear. Just similar thing, but in the reverse way. Okay. You can see here that what I get from what I've written here, this is G, X and Y, right? G, X and Y, I am finding X plus Y equal to at I. So G, X plus Y, I, this is Gx, this is a part of X, this is part of Y, two configurations, right? Ri, X plus Y, then Ri, this I get. So from this step I can write this one, because Ri is assumed as linear, since hence additive. So Ri, this X plus Y equal to Ri X plus Ri Y for the definition. So I write from this one, I can get G of X at I plus G of Y at I. So G is additive. Similarly, we can prove that we can say similar way. Alpha 2 is S, that alpha 2 into Gx equal to alpha 2 into Ri of this one. Then since Ri is linear, from that I can write Ri alpha 2 into this one. And so G into alpha 2 into X at I. So it's homogeneous of degree 1, right? And this completes the proof. So Ri, if each Ri is linear, then G is additive as well as homogeneous of degree 1. So it is linear. So therefore, to understand whether a CA is linear or additive, it's linear or not, we have to check only the rules of the CA, nothing else. This is the meaning of this theorem. Right. So let us now consider the non-uniform ECA. There are 8 linear rules in case of ECA. Okay, here they are written, right? So they are written. Suppose it is rule XYZ. I have written in format of XYZ. R is the rule. See, rule 60 rule is linear rule. I think you can recall that in case of ECA, we represent the rules giving the number called rule form numbers. It's like 90. In the previous example also, we dealt with 90, 150. So 90 is a linear rule. 150 is again a linear rule. How I'm getting so? Because they use the XOR. XOR means it's a mod 2, modulo 2 addition, no? So XOR means X plus Y modulo 2. You can check it. So let me give an example. So go back to rule 90. So that example, oh, that example is there. In the Jamboard, oh no. Okay. See, these two CAs are linear. You can check it. You can check it. See here, 3 inputs are there. L, S, R. Here I am considering X, Y, Z. Okay, that looks better. So I'm considering here X, Y, Z. Let me use different color. So how it will work? No, it is not visible. Okay. So here I'm considering it is X. So L, I'm considering it is X, it is Y, it is Z. So each rule R, it has 3 arguments, X, Y, and Z, right? Y is the middle one, Z is the left one, right? Z is the right one, X is the left one, this way. Now you see here, in case of 90, I claim that rule 90 means 90 has 3 input, X, Y, Z. See, this 90 has a function here. Huh? I have used 90 as function. So 90 has 3 arguments because 90 is the rule actually. So my 90 is not a simple decimal number. My way of representing a rule. So 90. So 90, it is having 3 arguments, X, Y, Z. See, you can check it is nothing but X plus Z mod 2. You can check. See here, X is left and right. 0 plus 0 is 0. 0 plus 1 is 1. Mod 2 is 1. 0 plus 0 mod 2 is 0. 0 plus 1, 0 plus 1 mod 2 is 1. 1 plus 0 mod 2 is 1. 1 plus 1 is 2. And mod 2 should be 0. It is 0. 1 plus 0 mod 2 is 1. 1 plus 1 mod 2 is 0. So therefore, rule 90, I can express this one x plus z mod 2. This is nothing but XOR operation that I have written, right? So, so it's showing that this additive rule. Okay, you can check with other thing. I'm not going in detail. That you can check. It is the additive rule. So if you can represent in this fashion in terms of XOR, then the rule is additive, right? Okay. So I am saying that if a rule can be expressed in this case, if rule can be expressed by XOR logic only, then it's linear. Here, I'm able to express this one. So similarly for 150, so rule 150, it has three argument x, y, z. I'm writing here, sorry, z mod 2. You can check it. I know it, so I've evident. Okay, so you can check. So 0, 0 plus 0 plus 0 is 0, no problem. 0 plus 0 plus 1 is 1, no problem. 0 plus 1 plus 0 is 1, no problem. 0 plus 1 plus 1 is 2, mod 2 0. Here also 1 plus 0 plus 0, it is 1. 1 plus 0 plus 1 is 2, so mod 2 is 0. 1 plus 1 plus 0, it is 2, mod 2 is 0. 1 plus 1 plus 1, mod 2, it is equal to 1. So it's rule 50. So actually it's nothing but x. So the rules that can be represented by XOR logic only, they're the linear one. So how many rules I can write? I can get, there are three variable. Okay, so total number of linear rule possible which can be expressed in XOR logic to the power 3 equal to 8. So there are 8 linear rules. How can I get? Here I get x XOR z is one rule, is 90. X XOR y XOR y, x XOR y XOR z, another rule, 150. In this way, only x XOR y, another rule, y XOR z, other rule. Okay, in this way I can get 8 such rules. These are written here. These are written here. Okay, so here see, you can check that linear rule 60 x or y, 90 x or z, which you have shown. 102 it's y or z. 150 x or y or z that you have shown. Last four rules, 170 is nothing but z, just shifting. It just is a shift rule. 170 is a shift rule. Okay. Actually, in default, it is actually XOR. You can write Z XOR 0, right? The same thing. And 204 is called identity rule. It is always Y. Okay. And 240 is X. And 0 is 0. So these 8 rules are the linear rules. If I put complement, okay, what is function, this logical expression x plus y, x or y, then actually I mean x nor y, then I get another rule, right? These rules are called complemented rule. Okay, this name was coined to study only non-uniform ECS. Okay, they have very interesting property. They are not linear but very close to linear, because you can see here 195, rule 195, from 60 by putting a knot you can get it, right? So it's in the so they are very popular, and they can be characterized easily from the calculation tools of linear CA. And then it is 165, 153, 105, etc. These rules, right? So they're the complementary rules. We shall discuss about them a little bit in the coming classes. So I get a notion of complementary CA. Okay, you know, this notion was described and studied by Palchodhuri and their group and his group. So these are complementary CA. Here, the C is complementary CA. See, complementary CA is not a linear CA, right? It's not a linear CA. So in that way, it's non-linear. Okay, but specialty is very close to linear, almost linear. So in complementary CA, at least one rule is complemented rule and rest are linear. If it is so, then the CA is a complementary CA. And finally, the nonlinear CA, where at least one rule is nonlinear. Nonlinear means here by nonlinear I want to mean here the rule is not linear, neither linear nor complemented. Okay, out of these 16 rules here, which are shown here, out of these 16, no rule is chosen from these 16 rules. Apart from the 16 rules, if any other rule is chosen, okay, uh, then that C becomes rule vector. Okay, that CA is a nonlinear CA. I think I should stop here. Okay. So this is about. So today we have started from very general definition of non-uniform CA, right? Then we discussed about some subclasses. Finally, we reached to the finite non-uniform CA, and in particular, we have discussed, non-uniform ECAs. Okay, a non-uniform CA where the rules are on the ECA rules, and it's a very restricted class of CA, but it has been explored by a variety of researchers. Why it is so? I give some hints that it is so because this kind of CA, they can easily be used to solve some technological problems. Right? We shall discuss them. So our final interest is on this class of CA, which is elementary non-uniform elementary CA. This CA actually in literature by hybrid CA, we if not stated otherwise, by hybrid CA we mean this per class only, right? Non-uniform CA and the cells use ECA rules and finite, right? Okay, and linear C is very important because in throughout the 90s and after 90s also, you know, I'm seeing a major share of the non-uniform C research, that occupy, the major share is occupied by this linear CA. Linear CA is explored by very, different kinds of researchers, right? So